This is a Module 2B video on the reactions of 1,3-dienes. 1,3-dienes, or conjugated dienes, are generally more reactive than the individual isolated alkenes that we have studied so far. Due to the slightly higher energy of the HOMOs, diene pi bonds are more nucleophilic than the HOMOs of isolated alkenes. And in the later chapter, we will study the reactions of nucleophiles with the LUMOs of alkenes. And the LUMOs of 1,3-dienes are slightly more electrophilic than the LUMOs of isolated alkenes. In chapter 19, this is demonstrated in the textbook with two specific reactions. The addition of hydrogen bromide to the diene commonly known as isoprene gives a fairly good yield of a single isomer with the common name prenyl bromide. This work comes from the lab of Stuart Warren, who was the doctoral advisor for the lead author of our textbook, Jonathan Claydon. It's quite possible that Claydon even conducted this reaction a few years after this work was published, as Claydon's doctoral work continued some of the earlier work described in this paper from 1985. What is remarkable about this transformation is that only one isomer was isolated. And there are several other isomers that were not observed. We can propose a mechanism for the hydrogen bromide addition following the principles established in the previous module. I will show the first step of two possible mechanistic alternatives in the space below. And then we can discuss how the evidence of product identity may support one of the mechanisms or disprove one of the mechanisms. And then in class, we'll discuss this in a claim, evidence, reasoning format. Moving the slide up. The first alternative is that hydrogen bromide protonates the more highly substituted alkene. As you know from previous work, the more substituted carbocation is thermodynamically favored, and so the tertiary carbocation is shown. Furthermore, this tertiary carbocation has positive charge delocalized, and this is shown in two resonance forms. The other possible mechanism begins with protonation of the monosubstituted alkene. As we've previously established, that secondary carbocations are more stable than primary carbocations. The proton gives a methyl group, and the secondary carbocation is also stabilized by resonance delocalization. Turning to the next page of the worksheet, this depicts the addition of diatomic bromine to 1,3-butadiene, another example from our textbook. In a paper published just a few years ago, the detailed experimental procedure showed that slow addition of bromine to a chloroform solution of butadiene at low temperature, and then allowing this to slowly warm to room temperature, concentrating the solution to reduce the amount of chloroform solvent present, led to the formation of crystals. The crystals were collected by filtration. This process was repeated several times, repeatedly collecting crystals as they formed, and they claimed a quantitative yield of 1,4-dibromo trans 2-butene. This is in contrast to the textbook, which claims that 3,4-dibromo 1-butene is the kinetic product, and that upon heating, 1,4-dibromo trans 2-butene is the thermodynamic product. That was based on work from the late 19th century, when their analytical capabilities were quite primitive relative to the 20th and now the 21st century. The fact is, in solution, a mixture of both isomers forms. In chloroform solution, the ratio of isomers is about 4:1. And so it's not clear that one isomer is strongly kinetically favored. I'll show a mechanism that gives a common intermediate which allows formation of either isomer. The module 1 mechanism involves formation of bromonium ion, and then the bromide anion can add in several possibilities. Either of these first two possibilities gives the 3,4-dibromo product. This reaction is reversible. The other alternative is that bromide adds at the opposite terminus. Here I've shown all of the arrows for accounting for electron movement. This leads to the 1,4-dibromo trans 2-butene product. This is also an equilibrium reaction. And now we can complete the discussion of this worksheet, scrolling down on the page to the claim that spectroscopic evidence reveals that the crystals are exclusively the 1,4-dibromo trans 2-butene isomer. There is additional evidence that we have discussed in this class in a general sense, which will support this claim. And in the class meeting, we'll discuss this additional evidence and the reasoning that links the claim of 1,4-dibromo trans 2-butene as the exclusive product when crystals are formed. This concludes the video on the reactions of 1,3-dienes.